All right, so for this next video, this is our demonstration project, RTDSP Project 3, we're going to be tackling on. So I've decided to tackle on both the flanging effect and the coarse effect at the same time, or in the same video, because these two effects are closely related to each other. So unlike with the graphic equalizer and notch filter, which are just FIR filters that we generated coefficients for in MATLAB and implemented in C, the flanging effect and coarse effect are a little bit more complicated. So we're going to first have to dive into a bit of theory about the flanging effect and the coarse effect. So as we look over here, so the flanging effect has a time varying delay. So the delay part, so it's going to be n minus, this minus part is going to be the delay, but the delay varies sinusoidally. And so a couple of parameters to keep in mind is R0 or R0, which is the maximum number of delay samples. We have F, which is going to be the discrete frequency. So when we think about the flanger effect, we think about that flanger echo having an oscillation or an oscillation frequency to it, or an echo oscillation frequency. And so this F is the discrete version of that. So if we take the analog version, or the analog frequency of the flanger echo and divide it by Fs, we would get capital F, which we would say is the discrete frequency. And what this is basically coming to is, this is basically coming to a point that, if you remember from Project 2, when we did the audio effects demonstration, the parameters such as the oscillation frequency of the flanger effect and the maximum delay, which were all given in terms of analog. But in order to be processed, they must be converted from analog to discrete. So we use a couple of conversions here to help us convert the analog values to discrete values. So the analog time delay is converted into the discrete time delay by taking the analog delay divided by TS. And as I mentioned earlier, you can take the analog frequency of the flanger effect divided by F of S to get the discrete frequency. Now this is important because we operate in the discrete domain, but our parameters are given in the analog domain. So depending on the sampling frequency, they can cause these values to change. So, like as I mentioned earlier, the delay is time varying. So that's a bit confusing and a bit complicated, because normally the delay is fixed for most of the FIR filters. So if the delay was fixed, it would create an echo, because it would essentially allow the same signal to appear but at a certain delay later. So with a fixed delay, it's an echo, but with this oscillating delay, it's the flanger effect. So in order to help us understand what's happening with the flanger effect, I did a bit of analysis in here. So originally in the instructions, you told us to generate the frequency response in the pole zero plot of the flanger effect. So now the problem, or I guess not really a problem, but the trick with the flanger effect is that since its delay varies, the number of poles and zeros that it has will also vary. So like in this MATLAB example, let's say the maximum number is 3. The maximum number of delay samples is 3. So that means that the transfer function will vary between the delay will vary between 0 to the maximum number of delay. And the transfer function for each different value of delay is different. So like it shows right here, for the different possible delays, we have different transfer functions. So if the delay is 0, or if the delay is 1, 2, or 3, this can go all the way up to the maximum number of delays. So what I did was I analyzed each of these 4 functions separately, just to observe the different effects. So obviously if z equals 0, then this is just going to be DC gain. There's no delay. So this is fairly straightforward. There's no poles and zeros, just simple DC gain. So now with the first value right here, we can rewrite the transfer function, and we see that we have our first set of zeros, or our first 0, and it appears at negative 0.8. Oh, that's tiny. See if I can zoom in. Actually, better yet, let me just run this. Let's run this in MATLAB real quick. Anyway, I forgot to talk about something real quick anyway, so I'll just briefly bring that up. So I talked about the delay, and I talked about the frequency, but I also kind of forgot to talk about alpha, or I guess I wrote it here as A, and that's basically the gain of the echo. It's fairly straightforward. If you have your gain at 1, then the echo will be at the same magnitude, or you can scale the echo to be quieter. Yeah, right here. This A value, the gain or depth, it's called depth in the WinDSK interface. Basically just makes how loud the echo wants to be. So in this MATLAB example that I did, I have the gain or the alpha set at 0.8 instead of 1, just because. So then I took the transfer functions for the different values. So this is transfer function 1, which is where it's a DC value because it's to the 0th power. This is to the 1st power, or to the negative 1 power. And this is to the negative 2 power, and so on and so forth. So what that does is, if I open up some of these plots, so the DC value, like I said, straightforward. No, it's straight. There's no poles, no zeros, no nothing. So the next one is we have a pole at 0 and a 0 at negative 0.8. Oh. And this creates a filter that looks like this, which has just one giant lobe in it. So if we increase the order, so now we have a delay of 2. We now have 2 zeros, one right here, and 1 pole, or 2 poles right here. So then the frequency response looks like this. So notice how we now have 2 dips right here. Dip right here, dip right here. So if we move on to 3, so notice you have a dip right here, and it looks like this. So the book describes these as comb filters because they look like the teeth of the comb, and as we increase the delay, the number of teeth in the comb increases, and these bands get closer together. So going back here, so yeah, that's what these pictures are. So a few important conclusions that we can conclude from this is that as the delay increases, you get more of these comb filters. And that I forgot to talk about the maximum value. So the maximum value is always the sum. So it's going to be 1 plus 0.8, and the lowest value is always the difference. So 1 minus 0.8. Let's see what else. Let's see if I forgot anything else I forgot to mention. So, and the peaks, yes, you have more peaks and more as you increase the delay. So the number of peaks right here is equal to the number of the number of delays. So here we have 2 peaks. This is half a peak, and this is a whole peak. So that's 2 peaks for a delay of 2. And for the delay of 1, we had 1 peak, and for the delay of 0, we had no peaks. And basically, if the delay keeps increasing, the number of filters, or the number of teeth in the comb filter, will increase. And eventually, these comb filters might be spaced. They're spaced every delay. Peaks are spaced starting with every nth delay. So the transfer function 4 had 3 delays, so that's why there are 3 peaks, and they're equidistantly spaced. 3 peaks right there. And so that's what that does. So that's what the changing echo is, because the echo would be one of these filters, but it would be constant because its delay wouldn't be changing. So to implement this in Code Composer, we won't need to generate coefficients in MATLAB because the flanging effect is not an FIR filter, it's an audio effect. So we have to do this all in C. So I guess first things first, we need to talk about sampling frequency. I've set the sampling frequency at 8 kilohertz. It's the lowest sampling frequency, so I'm not going to be using very many high frequencies. It also gives me the most time because I'm not going to do things the most efficient way. I do things the way that makes sense to me. And unfortunately, since I have not taken advanced C++ courses, I'm going to use a shift register and not pointers. So I removed the coefficients because we're not using those. So here's where things get different. Sampling frequency. So I set sampling frequency 8,000, so I set 8,000 here. So the analog delay, just like in the WinDSK, it starts in the analog delay in milliseconds. So if you remember how in WinDSK application, how it worked was the longer the delay, the I guess like the wider the whining effect sounds, if that makes sense. Well, I'll demonstrate. So if we have a large delay, 100 milliseconds, then you can expect the delay to, or you can expect the flanging effect to be very wide. And the flanging frequency is basically the frequency of the oscillation. I left that 2. Alpha in my simulation, I left it at 0.8, but here I just left it as 1. So then this is me converting it from analog to digital. So you see this is analog delay, and this is going to be the digital R naught that we talked about, which is the maximum discrete delay. And here we have this delay, but this delay is not really delay. This is more of a misnomer. This is going to be the discrete frequency F because it takes the flanger frequency divided by the sampling frequency to convert the flanger frequency into the discrete domain. Then I have the constant pi. All right, so here, again, we take the input, and the input's at the present value, and we store it in the, oh, I forgot to talk about the buffer. So over here, we have a buffer. The buffer stores R plus 1, just like normal. So this buffer is going to store as many values based on the maximum delay, discrete delay. And these test values don't do anything. These are just here to show the values because these are declared as defined, so it's hard to see their values. So these values are used mainly for debugging and won't be used in the actual application. So we have the present, we have the past, we have the output, we have a couple of variables right here. So this is the input, read the input, store the input in the present value, store the present value in the buffer. Now the maximum delay is going to be R divided by 2 because if you remember from our formula, since it's sinusoidal, it'll technically oscillate between 1 and -1. But we shift that. Let me scroll. But we shift that by 1, so that way it actually oscillates from 1, or actually oscillates from 0 to 2. So since it oscillates from 0 to 2, we need half the maximum, and so this angle is basically just the cosine part, or I guess it can be sine or cosine. I guess I should replace this with sine. But this is the sinusoidal portion. And so then you do 1 minus the sine part multiplied by the delay to get the actual displacement. Now this displacement must be rounded to an integer because we can only have integer discrete delay. So if you notice this is an integer, so this will round this to an integer. And so this is converted to an integer. And so then we take the value at that delay point and we multiply it by alpha, which I set as 1 in this case to be the past value. And so now we have to get to the output. So another thing was that if you remember the WinDSK interface, it had something called the wow effect. And the wow effect basically removed the present and only left the oscillating part. So we can do that by just doing the same thing here by removing the present, only outputting the past value if you just want to hear the wow effect. But right now I want to hear both the present and the past value. And this is going to be a shift register. Like I said earlier, this is not going to be a circular buffer. This is going to be a shift register because I'm not 100% proficient with pointers to create a shift or to create a circular buffer. So this counter basically is counting the sample number, so it increments each time. And so then it just displays the output and it's ready to go. So if I just debug this, all right. So if I run this, and if I take a sine wave and I play it, so you hear the tone which is the present value, but you also hear the oscillation on top of it. So you hear the oscillation right on top of it. If I change this to the wow effect by removing the present value, and I ran this again, now this should only give us the oscillating part, the oscillating echo. So now here we only have the oscillating echo part. So while I was talking about the whining, you can definitely hear where it's whining up and down, and that whining effect is more prominent when the analog delay is large. So if the analog delay was small, let's say the analog delay was only 5 milliseconds now. Oh, I think my signal ran out. It did. So I can bring it back here. So if I change the analog delay to only 5 milliseconds instead, and let's say I take this. No, I want to keep the echo loud so we can hear it. So I'll leave that alpha at 1. So all I did was decrease this analog delay to 5 milliseconds. I left everything else the same. If I run this again, so now when the analog delay is very small, so right here you can see it's really small, you don't get a very loud whine effect. It's more, sounds closer to the original tone, and so it's not like whining very loud up and down. So that's what changing this analog delay does. And obviously change this flanger frequency. So if I change this frequency to 1, then that'll make the oscillations appear slower. Let's say we have an analog delay at 20. Let's make the echoes a little quieter. And if I'm going to make the echoes quieter, I might as well turn off the wow effect so that I can hear the present value on top of the past value. All right. I run this. All right there. Turn this on. So here we see that because I increased the delay slightly, there's more depth to the whining. So you can hear a more whining sound. The frequency is lower, so that's why it sounds slower. And I've included the present value stacked on top of it. I included the present value stacked on top of the oscillation, so the original tone's right on top of it. And this is essentially all that there is to the flanger effect. Now the chorus effect, if we're going to go ahead and look at the next part real quickly, the chorus effect is basically 3 flanger effects that are added together. So if I look at our chorus effects right here, let me stop this. The chorus effect can be modeled by taking 3 separate flanger effects. So I have 3 analog delays, 3 analog frequencies, and I do all the conversions. Let me convert all these to sine. Doesn't really matter, they're both sinusoids, but so I take all 3 of these flanger effects, add them together, and the same thing, I can remove the present effect if I just want the wow effect. So, but in essence, it's almost exactly the same. I still have the counter that counts the sample number. This is all the same except it's just 3 flanger effects. So right now, let's say I want this delay to be 100, this delay to be 200, or 20. This one could be 40. Analog frequencies. Let's make this 1.5, 2.0. I have the gains, all these at 0.5. That's probably fine. Oh, I forgot that this should talk about, I still set the sampling frequency to 8 kilohertz just like before, matches this up here. There's no coefficients because we're not doing FIR filters, so everything is in the code this time, in the ISR code. All right, so this is the chorus effect. So when that's done, run this. So if so you hear the original tone, but you hear a bunch of oscillations all riding on top of each other because there's 3 flanger effects. I'll just play it for a minute. So this doesn't really sound like the chorus effect that we would traditionally expect, but we can generate the typical chorus effect by changing the settings on our flanger, on our different flanger effects. So like I said earlier, you can create tones that sound almost identical to the original tone by decreasing the analog delay. So that way there's not as much whining because the chorus effect doesn't have that whining oscillation to it. So by decreasing all these to 1, I've made it so that they sound less like oscillations and more like echoes. And then I'm going to change these analog frequencies to be harmonics of each other. And so if I do that and leave everything else the same, and I run this, all right. So now if I take a signal, you can now hear the chorus, because the chorus is actually composed of a bunch of signals that are all relatively close together. So this is what the chorus effect will sound like. So it sounds richer than just the single tone, but it doesn't have very strong oscillations. So you need a small analog delay. All right, so that's the chorus effect. And that's pretty much what it between these 2 special effects. So these 2 special effects, flanging effect and chorus effect, are not actually FIR filters. They are effects that are caused by changing by time-varying delay or time-varying echo. So we can't implement them using the basic FIR filter design. So they require a bit more theory and more coding, as you can see here, with the chorus effect and for the flanger effect. We have to actually code these values in and perform these shifting operations, or these time-varying delay operations. So that's all for the flanging effect and for the chorus effect, because in the frequency response, oh, I forgot to talk about the frequency response for the flanging effect. So real quickly, so I'm going to do a flanging effect simulation, and the same thing pretty much applies to the chorus effect. So the flanging effect simulation is that it basically gets modulated with a signal of that frequency. So if my tone is 500, or 500 hertz signal, but my flanging frequency is 2, then this becomes a signal with a frequency of 2. So you can see in 1 second it does 2 oscillations. And then this is the 500 signal writing inside of it. So that's what it does. It basically just does some modulation. If I look closely on the frequency response, it basically creates this, this spreads it out a bit on each side. So it creates, this is what the response looks like. So it looks like that, and it causes some spectral leakage around the stems due to the modulation. So yeah, that's the flanging effect. And the chorus effect is fairly similar. It's just going to do it 3 times and add them together, so it looks wavy. So here, I'll quickly look at the chorus effect. So the chorus effect is the same thing, but now since you have 3 different modulations stacked on top of each other, they're all going to interfere with each other, so it's not going to look as smooth. And so there's still now this around the different peaks. So this is at 4. There should probably be another one. So I started sampling frequencies. 1, 2, and 0.5. So this is what the frequency response looks like. It causes this leakage around the stems. And notice that, so the maximum delay when I did the course effect is only half. Oh, here it's half a millisecond. This one's 0.5 millisecond. This is 1 millisecond. So these are very short delays. So that would give us the course effect that we would expect, or that we would traditionally hear, where it sounds like a bunch of echoes. And notice how the amplitude of the modulation doesn't change very much. But if we went back to the flanging effect, I set the delay here to 1 millisecond. And so 1 millisecond looks like this, but if I increase this a bit, 100 milliseconds, now it looks a lot different. So you notice that the spectral leakage around each of these stems has increased. And if I decrease this back down to 10, then we get something that looks like this. So the frequency, or the maximum delay, plays a very vital role in the shape of the modulated waveform, which affects the sound. So for the chorus effect, we want very small delays, so that way they sound close together and can harmonize with each other. But if we want a large whining effect, then we want large sampling, or a large delay. So that's going to wrap up our discussion on the flanging effect and chorus effect. Next video, I will probably be doing the square wave and the square wave and PWM wave filtering together, because this is going to be a comparison between the two ways, or a comparison between filtering those two types of signals.